I should add a little bit more here. Why did we do this? When we looked at thermal winds, we expressed meridional gradient of temperature in terms of geostrophic winds and dTdP. I said it's convenient to think of vertical coordinate as pressure, but this has great relevance for the tropics. In the tropics, because of this deep convection and so on, the atmosphere is basically well mixed, and the temperature gradients tend to be very weak in the vertical. So relating the meridional gradient to the vertical gradient in the tropics helps, because it is what we call a nearly barotropic atmosphere. So the temperature gradients are weak. When we put that into this geostrophic shear equation, we can show that the geostrophic shear is actually zero in a barotropic atmosphere. So if the temperature gradient is constant in the vertical or with pressure change, then you have no geostrophic shear. So barotropic atmosphere doesn't have thermal winds. Okay? Which is what we started with, saying that we derive geostrophy with the homogeneous fluid, and then we have to worry about what happens when there is a temperature gradient or a density gradient. Let's go to the total column heating. The total heating of an atmospheric column Q bar T, the bar is always an average over space and time, depending on whether it's just space, just time, just longitude, just latitude, etc. In watts per meter squared, we can write it as a balance between net radiative forcing, which is short wave and long wave balance, and or the difference, and the sensible heat and latent heat fluxes. So here R bar net is the net radiation in and out of the column. So we are just imagining one column going from the surface to the top of the atmosphere. S bar H is the sensible heating of the column, so it's driven by the temperature difference, let's say between the surface and the atmosphere, or between two atmospheric levels or layers. And L bar P is the latent heating of the column from the release of latent heat of condensation, which happens typically during rainfall or precipitation processes. The differences in these net heating between adjacent columns is what gives us the buoyancy, differential buoyancy, and that can drive motion. Could be zonal or meridional. When we think about the energy transport from the low latitudes to high latitudes to balance the pressures, energy excess and energy deficit, we look for this body force that's going to be created by the buoyancy differences. That's what's going to drive the entire process of advection in the atmosphere and the ocean. Where does the latent heating come from? Obviously from the proportion of water vapor that converges into that column and precipitates. Right? So you have water density, latent heat of exchange, latent heat of condensation and evaporation, times precipitation, P bar, in meter cube per second. So you are looking at area and millimeters of rain, let's say, falling. So that's in meter cube per second as a volume of water. That's the total precipitation. So every time evaporation happens, energy is taken from the ocean or from the soil or the lake or whatever. Hydrogen bonds are ripped apart, energy is removed, so water cools, and that energy is put into the atmosphere. When the water vapor condenses, that energy is released, right? So if you think about the air column then, just as a grid going from n-1 n to n+1, discretization, energy released by the rain as we saw here, latent heat being brought in and taken out, or being advected in horizontally. So this is the schematic representation. The sensible heat is simply related to heat capacity, density, and WT bar. This is the exchange, vertical exchange of heat, energy, enthalpy. Various names are there based on what specific context it is. How does it work? If there is a temperature difference and there is vertical motion induced by the difference, to smooth out the gradient. Nature doesn't like gradients. Then let's say turbulent exchanges happen with which these gradient removals happen. You can write that Wt term as W bar plus W prime. Let's say there is a background wind over which this turbulence is happening, and the temperature also has a mean and a perturbation. By definition, W prime T prime average is going to be W prime average is going to be 0 and T prime average is going to be 0. So the W bar T W prime D bar and W bar T prime terms are going to go 0 when you average. So you're going to be left with the mean advection of the mean temperature and this so-called eddy covariance. Eddy is a term for these small scale motions. Small scale is relative, so I have to be careful. So if there is a high correlation between W prime T prime, then there is going to be a net exchange of heat, sensible heat in this case. So that's what we are looking for. S bar H is approximately going to be Cp rho times the average of W prime T prime. So these instruments which measure so-called eddy covariance fluxes, this is the term they're trying to measure. Okay, you can imagine the high speed processes that are needed to be done that. A similar derivation would give us latent heat flux as latent heat of evaporation or condensation times rho times W bar. This time it will be Q prime, W prime times Q prime, which is the humidity that's going to be doing the energy exchange. Okay, in the real world you usually measure mean quantities like wind speeds, temperatures, humidities that are either derived or measured, whatever, and you need what are called bulk formulae. So they are converted, these actual processes are converted in bulk aerodynamic formulas as Cp rho times some let's say a drag coefficient for the wind times the magnitude of the wind speed times the temperature difference in the mean, and latent heat as the latent heat of evaporations times rho times this drag coefficient times wind speed, and humidity difference between let's say the ocean and the atmosphere. So that gradient of humidity, so saturation humidity at that sea surface temperature and air humidity that's present, is going to determine the latent heat exchange. Okay, this is obviously a nonlinear function of temperature, so latent heat is obviously much more of a nonlinear energy exchange than sensible heat, which is a linear function in this case of wind speed and temperature difference. So let's leave this formulation there and come back to look at the actual distributions of exchanges of latent and sensible heat and freshwater fluxes which correspond to exchanges of energy as well.